derivatives can be used to find maximum and minimum values of functions. So here I've got a parabola. It has a minimum value at the bottom here. If it were the opposite way, then it would be a maximum. And in this example, I've got multiple peaks. Let's call these A, B, and C. C would be considered my absolute maximum because it is the highest point on the graph anywhere. A would be considered a local maximum, and B is a local minimum because while it is a minimum value, this function continues to go in the negative direction both ways. So it's not an absolute minimum. If this function had, let's say, gone back up this way, then none of these would be maximum or minimum, or absolute maximum or minimum values. They would all be local maximum and minimum values. In this example I'll get to in a second. So if I look at the places where there are peaks, and I think of it from the perspective of the tangent line, I'm going to notice that the tangent line is flat. And if the tangent line is flat, that makes the derivative equal to 0. So in order to find these places where I might have a maximum or minimum value, I'm going to take the derivative of the function, and then I'm going to look for places that the derivative is equal to 0. But it's still not quite as simple as that, and that's what leads into this last example over here. Here is an example where I've got a derivative that's equal to 0, but, well, it's not a very good line right there. The derivative is equal to 0, but there is no maximum or minimum value. There is none for this function. This could be a cubic function, for example. So now my goal is how to distinguish the maximum minimum value, so where the derivative is equal to 0, but to make sure that it's not one of these that just is a derivative of 0 but does not have a maximum or minimum value. So this is going to be the general procedure. It's very simple. So first I'm going to find f prime of x. Second, I'm going to find where f prime of x is equal to 0. These are going to be called what are critical numbers. A critical number is anywhere where the derivative is equal to 0. Now that can also include places where the domain of the derivative has like a hole in the graph, and would cause it to be 0 just because of something in the denominator, something like that. But for now I'm not going to worry about that. All I'm going to think about, let's just assume that there is no domain problems and it's just a regular polynomial, and I've got a 0 for my derivative. So once I have my critical numbers, then I need to figure out if they are local maximum and minimum values, or if it's something like this that has no maximum or minimum value. So in order to do that, what I'm going to do is I'm going to make a chart like this, and I'll use this example right here. So this one is going to have 1, 2, 3 critical numbers. I'm just going to do it without actually using a function, so I think everyone knows how to take derivatives now. 2, 3 critical numbers. That's a little bit far out. So let me start with this one first. If I look at the derivative of this function as it's coming down to this spot where it becomes 0, and I think of the tangent line, it has a negative slope, and then it starts slowing down until it gets to 0. And then it resumes in the opposite direction, getting quicker, but in a positive direction. So on this side of the critical number, the slope is negative. On the other side of it, it is positive. Now I'm going to go over to this example over here. Here, the slope is increasing, and it's positive. And here, the slope is also increasing, and it is also positive. But I have no maximum or minimum value. What's going to cause a maximum or minimum value is when there is a sign change. So now let me go to this example over here. Here the slope is increasing, and then it becomes flat. The slope is well, the slope's not increasing. I guess that's that would be the wrong way to put it. The slope is positive, but it's actually not increasing, it's decreasing. So the slope is going in a positive direction, and then it slows down until it gets to 0, and then it becomes a negative slope. Well, let me call these A, B, and C, rather than just critical number, critical number, critical number, A, B, and C. So this is how to go about doing it. It's really ugly. So I go on this critical number A. The slope is positive. Then on the other side of A, the slope is negative. It's decreasing. So this is what happens. Something like this. The slope is positive, and then it gets to 0, and then it goes to negative. So that's why there's this. If it were positive and positive, then it would go up like this again. Now for B, the slope is decreasing on the left side of it, then it gets to 0, and then it begins to increase again. So there's a minimum. The slope is increasing over here, and then it starts decreasing. So now it's like that. And if I want to find out which of these is the highest point out of all of them, what I do is just take the x value, or the critical number value, and I just put it back into, well, f of x, not f prime of x. And if I wanted to know if it was an absolute maximum or minimum value, then I would have to test all of the maximum and minimum values, find out what their y value is, and then if it's a closed interval, let's say if these didn't go down, it was just from here to here, closed interval from like A to B, then I would test the endpoints, find out what those y values were, and then see which one was the highest or the lowest if I'm looking for a maximum or a minimum value.